Thevenin equivalent. Tau equals R Thevenin times C. In the figure given over here, when the switch is connected to point 1, the capacitor will be fully charged. And when the switch is moved to point 2, the capacitor will discharge through the resistor R4. Now, the charging circuit over here is basically a complex network. So, in order to determine tau, which is time constant, we need to convert this complex network into a simpler one. And we can do that by using the Thevenin equivalent network. We need to determine the mathematical expression for the transient behavior of the voltage and the current for both the charging and the discharging phases respectively. And we also need to draw the resultant waveforms. In order to replace the complex network of the charging circuit by a simpler one, we apply the Thevenin equivalent theorem. R Thevenin in this case will be equal to 30 kilo ohm and E Thevenin will be equal to 7 volts. Now that we know the values of E Thevenin and R Thevenin, we can easily connect the capacitor to the Thevenin equivalent network and determine the values of VC and IC during the charging phase. During the charging phase, VC will be equal to 7 volts 1 minus e to the power minus t by 6 milliseconds, and IC will be equal to E Thevenin divided by R e to the power minus t by RC, which is basically minus t by 6 milliseconds. Or in other words, it can also be written as 0.23 milliampere e to the power minus t by 6 milliseconds. In the second part of the question, it was asked to determine the expression for VC and IC when the switch was thrown to position 2 at t is equals to 9 milliseconds. Now, in order to determine the expression for VC and IC for the discharging network, we need to determine the value of the voltage across the capacitor at t is equals to 9 milliseconds and the current at that point of time. So, using the given expression VC equals E Thevenin 1 minus e to the power minus t by tau, we can easily determine the value of VC at t is equals to 9 milliseconds, and that was equal to 5.44 volts. The current flowing through the circuit at that point of time was equal to 0.05 milliampere. Now, for the discharging network, Vf will be equal to 0 volt and Vi will be equal to 5.44 volt. So, using these values, we can easily determine the expression for the voltage across the capacitor in the discharging network, which will be equal to 5.44 volts e to the power minus t by tau prime. The tau, that is time constant for the discharging network, will be different from that of the charging network, because in the discharging network only R4 is present. Hence, tau prime will be equal to R4C, which is equals to 2 milliseconds. Then we can easily determine the expression for VC as equal to 5.44 V e to the power minus t by 2 milliseconds. And the value of current during the discharging period, the maximum value of the current during the discharging period is equal to 5.44 volts divided by 10 kilo ohm, which is 0.54 milliampere, and the value of IC will be equal to minus 0.54 milliampere e to the power minus t by 2 milliseconds. The continuous graph for the charging and discharging phase of the network will be as shown over here. The first graph shows VC against time and the second graph shows IC against time. The current of a capacitor is directly proportional to the rate of change of voltage across the terminals of a capacitor. That is, IC is directly proportional to dVc by dt. In order to remove the rate of proportionality, C is introduced in the expression, and hence IC will be equal to C dVc by dt. This states that the higher the capacitance of a capacitor, the greater will be the value of the resulting current. Capacitors in series and in parallel. When capacitors are connected in series, the charge is the same on each capacitor. That is, Qt equals Q1 equals Q2 equals Q3. Applying Kirchhoff's voltage law around the closed loop gives us the expression E equals V1 plus V2 plus V3. We know that V is equals to Q by C. Now, substituting this expression in the above equation, we get that Qt by Ct is equals to Q1 by C1 plus Q2 by C2 plus Q3 by C3. We know that Qt will be equal to Q1 equals Q2 equals Q3. Hence, dividing both sides by Q yields 1 by Ct equals 1 by C1 plus 1 by C2 plus 1 by C3. If two capacitors were connected in series combination, then the resultant capacitance would have been equal to Ct, which is equals to C1 times C2 divided by C1 plus C2. For capacitors in parallel, the voltage is the same across each capacitor and the total charge Qt is the sum of each of the charges on each capacitor. That is, Qt will be equal to Q1 plus Q2 plus Q3. We know that Q is equals to Cv. Substituting this expression in the above equation, we get that Ct times E will be equal to C1 V1 equals C2 V2 equals C3 V3. Hence, E will be equals to V1 equals V2 equals V3. Ct will be equal to C1 plus C2 plus C3. Now, for the given network, we need to determine the total capacitance Ct, then determine the charge on each plate, and at the last we need to find the voltage across each capacitor. Since the capacitors are connected in series, therefore the total capacitance Ct can be determined using the following expression. That is, 1 by Ct equals 1 by C1 plus 1 by C2 plus 1 by C3. In this case, Ct will be equal to 8 microfarad. The next question is determine the charge on each plate. And the third or the last question is find the voltage across each capacitor. Now, note that in series configuration, the charge across each capacitor is equal. That is, Qt equals Q1 equals Q2 equals Q3. We know that Q is equals to Cv. We already know the source voltage E and we also know Ct. Therefore, we can easily determine Qt, which will be equal to 480 microcoulomb. Now, we know the charge across each capacitor and we also know the capacitance of the capacitors. Hence, using the same expression, that is Q is equals to Cv, we can determine the voltage drop across each capacitor. V1 will be equals to 2.4 volt, V2 will be equals to 9.6 volt and V3 will be equals to 48 volts. In this example, the capacitors are connected in parallel configuration and we need to determine the total capacitance, the charge on each plate and the total charge. Now, since the capacitors are connected in parallel configuration, therefore the total capacitance Ct will be equal to C1 plus C2 plus C3, which is equal to 2060 microfarad. In order to determine the charge on each plate, we need to determine the voltage across each capacitor. Now, we know that in parallel configuration, the same voltage will be across each branch. Since we know the values of C1, C2 and C3, then using the expression Q is equals to Cv, we can easily determine Q1, Q2 and Q3. which will be 38.4 millicoulomb, 2.88 millicoulomb and 57.6 millicoulomb. The total charge Qt will be equals to Q1 plus Q2 plus Q3, which is equal to 98.88 millicoulomb. The energy stored by a capacitor can be determined by using the following expression, that is Wc equals half Ce square. In general, Wc equals half Cv square, but it is also possible to determine the energy stored by a capacitor in terms of Q and C. We know that V is equals to Q by C. If we substitute that over here, then the expression for the energy stored by capacitor becomes half C Q square by C square, which is basically equal to Q square by 2C.